All right, guys. Today in honors chemistry, we are going to talk about spontaneity. So let's get into our notes really quick. So you should be right here where it says spontaneous reactions. It's right where we left off, where we finished with Hess's law with the summation law. So spontaneous reactions, we're going to talk about what makes a reaction spontaneous today. And the idea of spontaneity is different in chemistry and physics than it is in our normal vernacular in English. So in our normal vernacular in English, if you say something's, we want to be spontaneous or whatever, you do things without thought. You do things kind of the spur of the moment, a whim. Now, in chemistry and physics, when we talk about things being spontaneous, that means that reaction will go forward and continue until it's done without any extra input of energy. Okay? So, spontaneous reactions are a physical or chemical change that once begun occurs without any further outside interaction or intervention. Oh my gosh, I can't spell. Intervention. Okay, so for example, and I wouldn't do this, but if I poured a can of gasoline on the floor, that gasoline's not going to burn. But if I threw a lighted match on that gasoline, it would burn until all the gasoline is consumed. Now that reaction is spontaneous, but I need to get it started. So once it's started, once that reaction has begun, I don't need to do anything else to keep that reaction going. I don't need to put in any more energy. I don't need to create the right environment. It will keep on going. Now, another thing that we think of in our normal English vernacular of spontaneity is it's relatively quick, it's relatively fast. Now, just because something's spontaneous doesn't mean that it is a quick or a fast reaction. Let's take another example. We all know how fossils are formed. We have the bones from the dead animal, usually a dinosaur, not always a dinosaur, but usually a dinosaur, that have become embedded and encrusted in some kind of a place where the calcium of the bones is not being eaten away. And over time, as the calcium in the bones becomes part of the rock, as liquids go through that rock and percolate through that rock, those different liquids, the minerals in there, change places or swap places, the ions swap places in the bone to actually make that bone now part of the rock. And it makes that, it's a chemical process, but it takes millions of years for that to happen, thousands, if not millions of years, for those bones to become encapsulated in rock, have the mineral exchange as the water is going through the rock, and actually solidify and make those bones fossilized. It's a spontaneous reaction. I don't need to put any energy in that for that to happen. It happens naturally, but it takes millions of years. So just because it's spontaneous doesn't mean it happens quickly. Okay? Let's go into see what is spontaneous and what nature says is spontaneous. So nature goes into two different directions spontaneously. Okay, so first we're going to consider energy or heat in a reaction. Now, I want you to think of yourself as this person in the middle of a hill on your bicycle. If I just plopped you in the middle of that hill on your bicycle and I told you to not pedal, to not do anything with your bike, where would you end up? That's right, you'd end up at the bottom of that hill. So nature, excuse me, that was my dog. Nature tends to take things from a high energy to a lower energy state spontaneously. So we go from high energy to lower energy. Nature is always trying to get to a lower energy state, always. So if we think about this, enthalpy is a good measurement of energy. So when we think about spontaneous reactions, our delta H is going to be going lower. So we would expect reactions that have a negative delta H to be spontaneous, because we are going to a lower energy in the system. Okay? Now, the next thing is entropy. And a lot of you guys have not really heard of entropy. So I want to define entropy for you here. Entropy. Now, entropy is a measure of disorder in a system. It measures disorder. Okay? So I want you to think about your room at home. Okay? Your room at home probably would take, if you're a typical teenager, it would probably take significant amount of energy and time to get your room to be spick and span and nice and clean, like Architectural Digest ready. Okay? Now, think of it this way. It's also a bit of chaos because we're measuring order. So this is a measurement of chaos in a system. So you can also think of it as measuring chaos. Okay? And it's a probability measurement as well. There are only maybe 2 or 3 ways that your room can be organized, and truly organized in a way that you would feel comfortable having a photo shoot of your bedroom being on Architectural Digest. But there are thousands, if not millions, of ways that your room could be organized where it was messy or unkept or whatever. So there are more ways, there are statistically more chances for disorder than there are statistical chances for order. So because of that statistical chance for that favors disorder, nature tends to go into disorder. Okay? So nature tends to favor disorder. Because even if you spent all that time and energy getting your room together, you would have had to spend energy to do that. And spending that energy to do that, you would have taken the food that you ate, which was relatively ordered, and you would have created disorder by burning that food and creating carbon dioxide and water, which has more molecules that are in the gas state and flying around a lot more than your orderly, say, sandwich or whatever. So even in the bid to clean up your room and make it orderly, the overall system becomes more disordered because you created disorder by burning the food that you used to create that energy, to create the order. Okay? So nature always favors disorder. Here's another example of this. Now, this is not my sock drawer. This is Mr. Hummer's sock drawer, my mentor, who I started teaching chemistry with. He says that he normally keeps his socks like this because it's a lot easier when he's done with his laundry to just dump his socks in his drawer. He told me that in order to get his sock drawer to look like this, where he had all his socks lined up according to type and size and color, took him a good 5 to 10 minutes to organize this. Notice this can only really be organized one way. There are millions of ways that the disorganized sock drawer can be organized and still be disorganized. Okay? So once again, it's the probability, it's the energy of keeping things orderly. Now, we know that in biology, in order to keep an animal or a plant or some biological system alive, it has to consume energy. And that energy, that food, we use that energy to keep the order in that system, to keep it repaired, to keep it functioning. Once that animal dies, it starts to decay and become much more disordered. Okay? So, the tendency towards increased entropy or chaos or disorder is summarized in the second law of thermodynamics, and you'll see that a lot in physics, which states that spontaneous processes always proceed in such a way that the entropy or the chaos or disorder of the universe increases. Okay? Entropy is sometimes considered to be a measure of disorder or randomness of the particles that make up a system. Particles that are more spread out are said to be more disordered, causing the system to have greater entropy than when the particles are closer together, because there's more ways that I can have them spread out than I can have them close together, right? Order. Recall that the change in enthalpy, delta H, for a system is equal to the enthalpy of the products minus the enthalpy of the reactants. Okay? We can calculate that with our tables for almost any reaction. There are tables out there all over the place that we can use. The change of entropy is the same type of thing. The delta S, and we do entropy with a delta S, is the change of that entropy of a system is the delta S of the products, the sum of that, minus the delta S of the reactants. Okay? So we still use the same equation for Hess's law to create entropy of a system as well. Okay? So let's think about this. Look at how nice and ordered the solid is. These molecules are nice in lines. They're in a crystal orderly structure. The liquid, they're nice and close together. They're moving slowly. Well, they're moving in the solid too, but they're vibrating around a fixed point. The liquid, they can move across each other, but they're still close to each other. So there's still relatively few ways to organize them. But in a gas, they're moving quickly, they're spread apart. There's all kinds of ways that we can have this. This is way more chaos. Notice as we go up from solid, liquid to gas, we create more and more chaos, more and more disorder. Okay? So let's look at some of the following things here and see which of these things has more entropy or less. And let's see whether that entropy is increasing or decreasing in these systems. Okay? So when we measure entropy, and my computer is freezing, when we measure entropy, we also measure entropy at our standard temperature and pressure. It's called STP. We might have talked about it a little bit before. It's 25 degrees Celsius, and it is at 1 atmosphere of pressure. So all of these delta H's and delta S's are measured at standard temperature and pressure. Okay? So hopefully we won't have to wait too long for this to happen. I am sorry for the wait. Okay, let's just take a look at A, if you can still see it. We have example 7A. So we have chlorine fluoride gas plus fluoride gas going to chlorine fluoride gas. Okay, so in A, we have 2 molecules of gas on the reactant side. And then the chlorine fluoride, we have 1 molecule of gas on the product side. Which has more order? 2 things bouncing around or 1 thing bouncing around? 1 thing bouncing around. So that 1 molecule has more order. So as we go from our reactant to our product, we are actually becoming more ordered because we only have 1 molecule. So because it's more ordered, our delta S is going to be negative because we're creating order in that system. So for A, this is going to be negative delta S. So for A, we're going to have a delta S that is negative. I want you to look at B, C, and D and see if you can figure out what's going on with those. Okay? Guys ready to check? So B, we have nitrogen gas, and then we have nitrogen dissolved in water. Which is more orderly? This one's kind of tricky. The gas is actually more orderly because once we dissolve that ammonia in water, we actually have 2 types of molecules that are arranged and going around each other. So we are actually creating more chaos by dissolving that ammonia into water because now we don't have pure ammonia. We have ammonia with a mixture. So that is actually creating more chaos in that system by creating that mixture. Okay? C, we have methanol going from a liquid to being dissolved in water. Once again, a pure liquid then being dissolved in water with a mixture. Mixtures are a lot more chaotic. So this is a positive delta S here. Okay, here we have decane going from a liquid to a solid. We are going from a liquid to a solid crystal, which is way more orderly. So our delta S here, we are going to more order, so our delta S is negative. Okay? So next time, we are going to start talking about Gibbs free energy, and we're going to use water going to ice and back and forth to water as an example of how temperature actually affects spontaneity, whether things happen on their own. Have a great time. We'll talk to you later. Bye.